Okay, hi everyone. Welcome to the session. We're going to be listening to Vikraman talk about categories of mathematics.
Okay, so I'm Vikraman, but I also need to write this thing that I'm supported by. Okay, they tell me to write this thing, so wherever I go. Yeah, so thank you to the organizers and for this fellowship, which pays my salary and allows me to do fun things. Yes. Okay. All right. Hi. So I'm Vikraman. I'm at the University of Bologna, and I enjoy thinking about semantics of programming languages. After we saw a very beautiful course by Chris on category theory, and also some very nice lectures by Connor on how to do type theory, the purpose of one of the purposes of my lectures is to show you that they're the same thing, and really there's a useful way to think about categorical type theory or type theoretical category theory, and you can move ideas from one field to the other. Because I say semantics, so it's worth what exactly does this is very so I say semantics, but semantics means a lot of different things depending on where you go and who you ask. So when you I think the field of semantics has advanced a lot, and what if you went and asked a logician what is semantics, they would give you a different answer. If you went and asked a programming languages person what is semantics is, they would give you a different answer. And if you asked a category theorist what it is, they would give you a different answer. So I think the way I would say is there's semantics of syntax, and then there's semantics of actual programs, right? And then so semantics of syntax is when I give you syntax, but you look at it and realize, oh, it's actually an initial algebra of something. And then there are programs where you look at the program and you realize, oh, it's actually a mathematical function. Okay, and so there are lots of different things happening in semantics, and maybe one of the big pitch for category theory is it's an organizing framework for understanding what's going on with all these things. And there is of course the semantics of a program is what happens when you run it. It's another way of talking about semantics, but the kind of semantics that I want to talk about is more what I would say denotational semantics. So it's important that we say it's denotational, which is that programs are about syntax, but it's not necessary that programs are just pieces of syntax. When I write down a factorial function, it is literally computing a factorial function in some way, right? And when I think about a factorial function in my head, I don't think about a Haskell program. I think about a function on the natural numbers. Right? And so there is some sense in which programs do give you mathematical functions, and that's what I mean by denotational semantics. I would, so for me, because I started from logic and went into programming languages, so I do think that programming languages have logical foundations. Often they do, sometimes they don't. And it's important to sort of think of these things in the tradition of logic a little bit. so when it so in the history of logic, there's denotation. This whole thing came from Frege, and Wittgenstein thought a lot about these things as well. And if you look at the history of logic, there was a huge crisis when Russell gave Frege gave a bunch of rules, and people did not know how to present a logic. And Frege said, well, here are a bunch of rules, here are different bases for these rules. But I don't know anything more than that. And then Wittgenstein said, no, well, if you want to have a meaning for logic, you have to think of it denotationally. Okay, and so there is a certain sense in which there is a formula in logic, and there is a denotation for it. And so I think this is kind of the tradition in which the whole, I would say the what is semantics? It started from these people thinking about semantics of logic, and now we should maybe there's a lot of logical foundations in programming languages, and maybe it's worth thinking about them in different ways, starting from the beginning. And then logic is about provability, but programming is about programming, which is computation. And so when I say logic is about provability, but a type theory or a programming language has at least two different aspects. Okay, so I would say this is the algorithmic aspect, and then there's the logical aspect. Okay. So the algorithmic aspect is you run a program, it reduces, and you look at the reduction, and you observe the output. So it computes an algorithm. And then there's the logical aspect. I write down a type, and I try to program. I try to write a program of that type. Okay, and in a certain sense, these two things seem very different things at first, but it's almost as if the logical aspect sometimes undermines the algorithmic aspect, or the algorithmic aspect undermines the logical aspect. And types and the meta theory of a type theory actually tries to connect both of these things, as in things like type preservation and strong normalization and these things. And now, why would you? I find it interesting that category theory does in fact shed some light on how these two things are actually related. And the more you think of programming languages as objects and arrows in a category, they do give you some insight into what is actually going on in both in both of these things. So and yeah, but okay, so this is a bit of yeah. So we should care about programming language foundations for these reasons, like good foundational reasons. But then there's also what is the point of semantics for practical programming. So one important thing to say is that syntax doesn't have to be just we design programming languages and type theories all the time. Sometimes we come up with very clever ideas, like Connor showed us, and for me, it's a different point of view, which is that I think syntax should always be mathematically informed. You should do what the category tells you to do. If you are not doing the right thing computationally, it means the model is wrong somehow, and you have to fix the model. Okay, so I think syntax should be one mathematically informed. And the second thing is there is a whole aspect of language design. So syntax is just sometimes the core syntax of your language, right? And language design is much more than that, which should also, I believe, be mathematically informed. And sometimes thinking about semantics lets you, actually realize, oh, there's much more that exists in the semantics, and the programming language wasn't doing the right thing. Okay, so new language features are okay. Okay. Okay, so this is some propaganda, and at the end of my lectures, I'll try to show you that, yeah, it actually works, and I found it. Sometimes it works, often it doesn't work. You think a lot about semantics, and well, nothing is very good. Computers don't behave the way we think often, and we approximate, and yeah. Also, just to one other remark is, so I think all of this is just abstract mathematics, and both syntax and semantics, or type theory and category theory, are abstract mathematics, and each of us has different opinions about how we think about abstractions, and I find that it's very difficult to talk to people when they have a different point of view on abstractions, and we should really just be more friendly towards each other, and syntacticians and semanticists should talk to each other. So, like, personally, I enjoy going to talks and listening to what type theorists have to say. Then I go home and try to reconstruct all these things that they've been telling me categorically. Sometimes it leads to new insights. And the other thing is that often, I mean, we can do category theory, but I don't think the world is ready for category theories. Sometimes when we write papers, we have to actually hide the category theory, which is something Chris also mentioned. And this is not good, and it's just, I don't know what to do about it, but many of you might have opinions about it. But now that we are in a summer school, I don't want to hide the category theory. So this is the point of maybe coming here and talking to people. And yes, okay. And finally, I am doing things on the board, and I might make mistakes. So if you notice mistakes, many of you are experts in these things. You know a lot about these things. So just stop me and correct me. If I make mistakes, I wouldn't be able to sleep at night. So and yes, okay. And now I have a so I will plan a concrete plan for this lecture. Is I want to ask if in the empty context I write down this type, and I ask if is there an E which inhabits this type in the presentation of simply type lambda calculus that Connor showed us. Okay, so I believe someone asked this question. Yeah. So does anyone have an idea on how you do this, or do you think there's a program of this type? So A and B are two types that I assume are not equal. Yeah. Yeah, for all A and B, A not equal to B, is this type inhabited? No? Okay. Right, so. Okay, but how would you go about proving it? Right?
Perhaps not what you have in mind, but one way you could try to normalize it.
Yeah, right. So this is funny. I mean, I would say this is the French way of doing things. You look at the normal form, and Connor's system already has a very precise normal form. So you look at how you derive this thing, and there's no beta redex, and you do a case analysis, and there isn't derivation tree. Okay. So that's one way of doing things. maybe the other way is you build a model and you show that the simply typed lambda calculus has a nice class of models, and you prove a soundness theorem, and then you use the contrapositive of the soundness theorem. You exhibit a model in which the lambda calculus does interpret, but it doesn't prove this type, or doesn't have a program of this type, and then by contrapositive of soundness, you show that such term doesn't exist. Okay, so that's one thing. And the other thing which semantics is actually very good for is to reason about programs. Okay. Oh. Okay, sorry. Okay, let me, so if I write this program in the lambda calculus, okay. Yes. Okay. So yeah, so this is a lambda term, right? It's a function from booleans to booleans. You should try compiling this program using your favorite C compiler. And I tried to compile it, and GCC without any optimal, like with GCC 01, it actually generated a program which looks like it moves to EDI. So I'm simplifying a bit, but okay, I'm simplifying, but I just want to. So it's actually doing a comparison, and if then it jumps to L2, otherwise it does move X. Otherwise X over, or it jumps to L2, where it does where it just returns. Okay. So this is GCC if you don't add any optimizations. But if you add GCC with optimizations, it just does move X 0 and returns. If you want to do even better, you should try GCC 03, and and what it actually does is XOR EAX EAX. So XOR has a smaller opcode than this.
Yeah, you're a patch.
Yes. So in lambda calculus, this is the it becomes a constant function, right? So GCC is actually doing an optimization, and if you know enough category theory, you'll see that you can use the universal property of coproducts to justify what GCC is doing, right? And yes, yes, but there's something also. So there's like if you do a liveness analysis in this program, there are more live registers, and so the semantics that GCC is using is actually not very resource.
What do you get if you compile
Oh yeah, I get exactly this with O2, yeah, and with O1 I get the same. Yeah, so I mean, so yeah, I mean, it's actually so if you build enough machinery to reason about your lambda calculus program using category theory, you can actually justify compiler optimizations. But I want to there are of course other frameworks like syntactic frameworks which talk about observational equivalence, right? So I can build a context where I plug in this program, and then I have to do an induction on all contexts with an X. And if any of you have tried to do this, it becomes very difficult because for all contexts it's very hard. So the traditional tools for doing things operationally, using observational equivalence or applicative bisimulation, these things with the harder programming language or more complex programming language features, they become genuinely harder. And if you reconstruct these things using some basic tools from cache theory, they can actually be much nicer to do these kinds of reasoning about programs. And okay, and okay, and so that was the thing. And the final thing is I'll do a semantics for a real language, and real language which has effects and something called capability safety. Okay, so all of this is actually very much inspired by a real language which I have in mind, and I'll tell you about it at the end. And I'll build some tools and tell you how to apply these tools to actually do real semantics. Okay. Okay. So right. So. Okay, so I would like to start by giving just what it means to give semantics to logic. Okay, so the logic I would start with is intuitionistic propositional logic, which is just the logic behind the simplest SPLV. So we have truth and conjunction and implication. It's actually sub fragment of intuitionistic logic, which also has false and disjunction. But this is the easiest thing to do. What is if you open a logic textbook, you'll see different presentations of intuitionistic propositional logic. There is usually some propositions which consist of atoms like this, and then okay, sorry. Atoms, and then you add the connectives. So you say phi and phi, phi. Okay, and then different logic books do it differently. If you read a good logic book, it will it will do this thing, which is the hypothesis rule. So gamma is the hypothesis rule, and so I haven't said what it is. Okay, and okay, and yeah. Okay, so for every connective, we give a introduction, elimination 1, elimination 2, and then the implication would be produced as means okay. So this is a good set of rules. The nice thing about these rules is that you can yes. So the axiom rule and the Vikraman rule and so these substructural rules you don't have to add them to your logic, yes. But you'd see a different presentation in some books where you'd add these three rules, you forget about this, you have these rules, and then you show it actually admits cut elimination. Okay. But if you present your logic in this way and you show that actually cut is derivable, so it's not very surprising that cut, so gamma phi derives psi, you use arrow introduction to get your function type, then you eliminate using this argument, and that's how you prove cut. Okay, so cut is admissible, right? And yes, yeah. I did not add false because semantically it's hard. It's not the logic of a Heiting algebra, it's the logic of a Heiting semilattice, which is what I will say right now. I mean, so let's see. An interesting question to ask is there a semantics for this this logic? And the way a logic textbook would say is these things is like, so you have some atoms that you fixed, right? So given any formula, you can find some pre-variables, which are these free atoms, and you have to assign some. So let me say that this is a set of atoms, and there is a valuation function, and I need to. So it's logic. Everything is either true or false, right? So it's 0, 1. That's it, right? And so if you give me a function on the atoms, I can interpret any derivable sequent like this in V, right, as a function from. Okay. So the way you would define this is by induction. So when it's the let me just write a okay right. So first I need to define what gamma, the valuation of a context like this is. So at the empty context is 1, and gamma. Okay, so I will try to use, let's say, min. Okay, so it's the min of gamma. Okay, so you can, although I'm writing gamma derives phi, you can take, because it's a one-sided sequence, you can take the things on the left and just produce a formula by conjunction. So it's so the meaning of a context is the meaning of the conjunction of all the formulas in it, right? And then let's say, so phi and psi is again min I. Okay. And so it's 0, 1, and I want, if you, we know truth tables, so just say max of not sorry. Okay. And so this is a valid semantics. In fact, if you go and do induction, and you'll get a function like this at the end. What you would get is if a soundness of your semantics, which is that if phi derives psi, to 1. Okay, so this is certainly a sound semantics to have. Oh, sorry.
Yeah, I might be getting some of my intuitionistic and classical stuff wrong, but doesn't the interpretation of the sequent need to introduce negation in one of the things?
So yeah, I did a. There's no negation. You mean?
Yeah, but I think you implied that for interpreting the sequence, you can just lump everything together. And shouldn't like either phi or gamma be negated? The denotation of them. Oh, I thought you were talking when you were saying that you were talking about the interpretation of the turnstile.
The interpretation of the turnstile
should match the one for the implication, right?
Should match the one for the right. So I'm first. Okay. So first I interpret contexts. Okay. I interpret formulas. Then I state soundness. Is this okay? Right. So.
Okay. So when you do the mapping from, I guess
maybe this is maybe not interesting for now because I'm just talking.
Yeah, I was just thinking whether 0 is supposed to be an integer set and 1 is supposed to be one element set, or
no, they're just numbers for now.
They're
just numbers. Okay. Yes. But the point I want to make is that using numbers 0 and 1 for semantics is very bad. So the semantics that I wrote, it's actually very bad because well, I mean it's sound of course, but it so this thing. So like so if I have an if I take Pearson's law and I choose some P in 0, 1, Q in 0, 1 for any of these valuations, the meaning of this formula phi, or yeah, this is going to be 1. Okay, so the semantics isn't telling me anything about my syntax because the semantics equated too many things. Okay. So you look at it and then you think, okay, so somewhere in these equations I've made a wrong choice, right? And the way to so what structure of 0 and 1? I chose to just write things using min and max, but I wasn't thinking. Okay, yeah. Oh, you had a question. Yeah.
Okay. Yeah. So when you're giving the semantics, so the context and the meaning of the context and the conjunction are same, right? So like both reduces to like
yep.
Also, and the not just flips the thing, right? One. So it's in the meta logic, like so.
There's a not in the meta logic.
Yeah. Yes, so that flips the thing.
Yeah. 0, 1 to 1.
Right. Yeah.
Right. So the semantics is sound, but it doesn't answer our question on how to do Pearson's law. So it says Pearson's law is actually true in the semantics. So so we need to fix the semantics, right? And what am I going to say? So so this is not the right way of writing semantics. It's what people did 100 years ago when Tarski was trying to give semantics, and the first and then Tarski refined the semantics and said, well, given such a logic, I will look at its Lindenbaum. parse key algebra. Okay, so so let me just get rid of context because you could always do conjunctions on the left, right? So I will just write this, and so I have a collection of formulas. These proposition is all formulas, right? In my set of, okay, I think I defined a set called propositions, okay, and then I define a partial order. I define a pre-order on the set of formulas by saying phi is less than equal to psi. It's defined to be so phi is less than psi if and only if phi derives phi. So it's a partial order. So it's a okay. First, it's a pre-order. So it's reflexive, and you notice that by one of the structural rules, like axiom, it's reflexive. It's transitive. Okay, by cut it becomes transitive, and this is enough to be a pre-order, right?
Sorry, one more question. Like, so in this setting, you don't have false as a primitive. Like, you only have true and implication. So when I think about like, I mean, the denotation. If I ask, is there a formula for which I can get 0 in the denotation? I mean, earlier you mentioned.
There a formula for which I can get 0. A arrow B arrow A.
Okay. Oh.
I think.
So I mean, it's not like you should like yeah. So it's aimed. It's
yeah. I mean, P arrow
okay,
Q,
okay.
and you assign some truth valuation which will make the 0. It does exist.
Okay.
Because, yeah.
Thanks.
So reflexive transitive makes it a pre-order, right? And then I'd like to make it anti-symmetric because posets are nice to work with in pre-order. We saw some very nice properties of posets in Chris's lectures. So to do that, I will quotient the this thing by equivalence. So it might be the case that phi derives psi and psi derives phi, but they don't have to be the same formula. But logically, it doesn't matter. So I can quotient by implication to make them anti-symmetric. And then for each connective, I look at the rules and I try to see what it does. So the truth. So there was a comma derives truth. So for all p in this thing, p is less than equal to. So there exists. So there exists true in prop that for all p, p is less than equal to true. Okay, and for the conjunction connective, you notice that okay, you notice that this a compact way of thinking is that this is actually reversible. So if you know this and this, then you know this. If you know this, you can do this, right? And so you use that to notice for all p and q, there exists a p and q such that r less than equal to p and q if and only if r less than equal to p and equal to q. Okay, so that's one connective, and then you have row to and q if and only if so there is another connective for the implication, and which I'm writing with a double arrow, and yeah. So this, if you know about lattices and Heiting algebras, this is the greatest element, right? And this is the meat, and this thing here is a Heiting implication. Okay, and now the thing you want to show is that yeah. So from the rules of logic, I constructed an algebraic object. It's a pre-order. It's a poset with 3 additional things. And now, if I want to reason about my logic, rather than reasoning about my logic, I would like to reason about my logic using this algebra. Okay. So is this logic exactly? Does it exactly? So is there anything else that I'm missing? Well, we can do some induction to make sure we've got the right thing. So what I want to show is that if so there is now a the valuation function goes from a formula right. No, sorry. So first I fix a valuation function which takes from prop to these my variables, and let's call it prop with that name. So let's call it no LT. And so I first I need a valuation function which is going to send my propositional variables to this set, and there is a unique way in which every formula gets interpreted as a top element. Okay, so the canonical thing to do is to interpret each connected here, and given such an algebra, can I write down a logic for it?
Yeah. So actually, those the and the implication. I mean, those are the operators in the algebra, right? I mean, you have to so one is in the propositional logic, and yeah. So there is a suppression there, right? Yeah. So yeah, can you just write it down? What are all the operators in the?
Let's use a different symbol for the meat.
Yeah.
Let's say this is single arrow, and yes. So really, the point I want to make in maybe 5 minutes is that there shouldn't be a distinction between these two things, because there is a precise sense in which they correspond to each other, the way to make that very precise is to tell you that there is so partial orders plus these operations. These operations are true. Okay, so let me call them Heiting semi-lattices Okay, so Heiting algebra has disjunctions, but I'm dropping disjunctions, and so that's why I'm calling it a Heiting semilattice. And so it's a set which has some elements, and these elements are closed. It has a partial order, and you can state the axioms with these connectives. And so what essentially the whole thing is trying to say is and then given two such so p less than 2p into p minus p q less than q. Okay, so if I give you two such Heiting semilattices, I can write down what are the maps between them, and so the maps should map the sets. So these should be functions on the sets. They are full sets, so they need to be monotone for all q. If p is less than or equal to xy, x is less than or equal to y in p, then f of x should be less than or equal to f of y in q. Okay, and that's the first thing from being a poset, and then f of this should be this, and f of x int y x int y, and it should preserve Okay, so this is a homomorphism between these two Heiting semilattices. And all of this data, you can see that it has identity and composition, right? So it sets with a poset relation, which is monotone, and then monotone maps, and then additional structure, which is preserved. So now I can build a category of Heiting semi. So I'm sick of writing semilattices, so that's just Heiting algebras, right? So there's a category of Heiting algebra. Okay, this is the thing where objects are these things, and maps are functions between them which preserve structure. Okay, and now given such a Heiting semilattice, what I get is every Heiting semilattice comes with an underlying set. So because these functions are just set functions, I can build a underlying functor which gives me the underlying set of the Heiting algebra. Okay, and this thing has a that's my well, but let's just say f. Okay, so we learned about adjunctions in the category theory class. So what this is saying is that maps out of the free thing on some underlying set to some other Heiting algebra, let's say P, are in bijection with functions from X. So set has functions. So writing set U so I'm ignoring the U because U just gives me the underlying thing. But so I don't need to write. So okay, let's just write P. So P is the underlying set. But, it's really U of P, but I'm ignoring the U. So so what more concretely, if you remember the definitions of adjunctions, so given any set X and a map giving a valuation function on the set of atoms to this Heiting semilattice, there is a way to extend it to the free Heiting semilattice on the set of atoms X, and let's just call it map eta, such that there is this semantics of formulas in f of x. So formulas in f of x are exactly these things. So propositions which are identified by implication, and they go to P. Okay, so to give a model of this logic is to give a Heiting semilattice, right? Because an evaluation function, right? So all I have to do to refute so I'll maybe just do it in 5 minutes, but it's too quick to do in 5 minutes. So to give a model of this logic is to give a evaluation function, and it has a canonical extension by the universal property. Okay, so so I want to now give you a P. So I have to give you a P, a Cartesian closed coset. I haven't said yet. So a Heiting semilattice, and I have to give a evaluation function, right? So so let me take my original formula. So now, can someone give me an example of a Heiting semilattice? Maybe that's the hard part, right?
Any Boolean algebra.
Yes, any Boolean algebra. So the thing so 0, 1 with not, min, max. So that was the semantics I started with, where I was interpreting this P as not P max, not comma Q. Right? So when I used this as the semantics, it was not a good semantics. Is there a different, do you have a different example of a Heiting semilattice? Yes.
I think power set, like subset and then power set.
Okay, so what set should I? Okay, so power set of A, C, and I need a less than equal to relation, so I should use subsets. Okay. Okay, so is there a way to refute this? What values would you assign PQ to refute this thing?
So what we should do to use a subset of our own data.
Okay, so it looks like this this is a Hesse diagram of the process. And then the meat of these two things. So so this thing only had 2 elements. This has a bunch of elements.
No, I guess the question.
Yeah.
My question is, what's the binary operation for?
Yeah. Okay. So this was something. Right. So for power sets, the meat of two, let's say S and S and T is S intersection T, and and what should this be? I guess. So when it's power sets, you have complements. So S complement union T. That's one guess. But unfortunately, it's also a Boolean algebra if you do it this way. So you'd end up with the same problem. And yeah, so.
How about the line?
Okay, yes. So line with, so you want a continuous?
No, I just thought like 3 points.
3 points, yes, very good.
Yeah. Can have a continuous one.
Yes, 3 points. That's the thing. So we were restricting ourselves to 2 truth values, and we now have 3 truth values. And yeah, and now I have to really define the meet operation. And well, I know the formula to define it because I can because I know it, but you have to be a little bit clever in coming up with a definition. So like what you want to say is P and Q should really be the smaller thing of Q, right? And I hope I am right. If so, when you have a linear thing like this, you should set it to 2 if P is less than or equal to Q. Otherwise, you should set it to Q. Otherwise, okay. So exercise, verify this is a writing semilattice with these things, and number and the second thing that you want to check is the meaning of this formula phi, following the equations of interpreting this logic with so find the evaluation for P and Q such that you know, so the true things in this is the number 2, but you can find the valuation such that this is not going to be, this is going to be less than 2, literally less than 2. Okay, so this is an exercise. We can talk about it after the after it's over. Yeah, but yeah, so it's generally hard. Like it's hard to come up with you know, these things, but you can use category theory to do this very easily, and that's what I'd like to do next. But because of lack of time, I think I'll stop here.
Thanks, Benjamin. There's maybe somewhere something that questions.
The microphone is here.
Okay.
What?